I've been thinking a lot about the simulation hypothesis lately, this idea that we might be living inside some kind of computer simulation. And it's one of those thoughts that once it gets into your head, it's really hard to shake out. Because on the one hand, it sounds absolutely ridiculous, right? Like something out of a science fiction movie, the kind of thing you dismiss immediately as paranoid conspiracy thinking or philosophical navel-gazing taken way too far. But on the other hand, and here's where it gets uncomfortable, when you actually look at the arguments, when you really dig into the reasoning behind it, it's not nearly as easy to dismiss as you might think. In fact, some very serious philosophers and scientists have argued that not only is it possible we're living in a simulation, but that it might actually be more likely than not. And that's deeply weird. So let's start with the basic intuition here, because I think most people, when they first hear this idea, have a pretty strong reaction. It feels wrong, doesn't it? It feels like the world around us is clearly real, solid, tangible. You can touch a wall, you can feel the sun on your face, you can taste food, experience pain, feel emotions. All of that seems to have a fundamental realness to it that can't possibly be simulated. And I mean, I get that reaction, I really do. There's something in us that rebels against the idea that our entire existence might be essentially a very sophisticated video game. It feels insulting somehow, reductive, like it diminishes the significance of our lives and experiences. If we're just characters in someone else's program, then what does anything matter? What's the point of any of it? But here's the thing, and this is where you have to kind of set aside your emotional reaction and think about it more carefully. What would it actually mean for something to be a simulation? And more importantly, how would you know the difference? Because if a simulation were sophisticated enough, if it were detailed enough, complex enough, internally consistent enough, then from the inside, from the perspective of entities existing within that simulation, it would be indistinguishable from what we call reality. Think about it this way. When you're having a really vivid dream, while you're in it, it feels completely real, doesn't it? You don't know it's a dream until you wake up. The experiences you have in that dream, the emotions you feel, the things you see and hear, they all seem genuine in the moment. Now, I'm not saying we're in a dream, that's a different thing entirely, but it illustrates an important point. The subjective experience of realness doesn't necessarily tell you anything about the underlying nature of that experience. And that's where the simulation hypothesis gets its foothold, in that gap between subjective experience and objective reality. Because really, when you think about it, everything you know about the world, everything you've ever experienced, is mediated through your senses and processed by your brain. You don't have direct access to reality as it is in itself. You have access to your brain's interpretation of sensory data. And if that's true, if we're always one step removed from direct reality anyway, then how would you know if that sensory data was coming from a physical world or from a simulation? What test could you run? What observation could you make that would definitively tell you which one it is? That's the unsettling thing about this idea. It's not just wild speculation. It's actually a pretty serious philosophical problem that people have been grappling with in various forms for thousands of years. I mean, Plato had his allegory of the cave, right? These prisoners chained up, watching shadows on a wall, thinking those shadows are reality, not knowing there's a whole world behind them that they can't see. That's basically an ancient version of the simulation hypothesis. And Descartes, when he was doing his methodological doubt thing, when he was trying to figure out what he could know for certain, he imagined an evil demon that was deceiving him about everything, feeding him false sensory experiences. He came up with, "I think, therefore I am," because that was the only thing he felt he could be certain of. Everything else, all the external world, could potentially be an illusion. And we've had variations on this theme throughout philosophy. The brain in a vat thought experiment, for instance, where you imagine a brain kept alive in a vat of nutrients, connected to a supercomputer that feeds it sensory experiences. From that brain's perspective, it would think it has a body, that it's moving through the world, having a normal life, but it would all be generated by the computer. So the idea that our reality might not be what it seems, that we might be experiencing some kind of artificial or simulated world, that's not new. But what is relatively new, what's happened in the last few decades, is that we've started to develop the technology that makes this idea seem not just philosophically interesting, but actually plausible. We've built computers, We've created virtual worlds. We've made video games that are increasingly realistic, increasingly immersive. And when you look at the trajectory of that technology, when you see how far we've come in just 50 or 60 years, it starts to seem, well, almost inevitable that eventually we'll be able to create simulations that are complex enough, detailed enough, that conscious entities could exist within them and have no idea they're simulated. And that's where Nick Bostrom comes in. Bostrom is a philosopher at Oxford, and in 2003 he published this paper called Are You Living in a Computer Simulation? And it's this paper that really brought the simulation hypothesis into mainstream philosophical and scientific discussion. Now, Bostrom's argument is actually pretty elegant, and it doesn't claim that we definitely are in a simulation. Instead, it presents what's called a trilemma. It says that at least one of three propositions must be true. Either first, civilizations like ours almost always go extinct before reaching a technological level where they could create realistic simulations of conscious beings. Or second, civilizations that reach that level almost never have any interest in running such simulations. Or third, we are almost certainly living in a simulation right now. Those are the three options, and according to Bostrom's argument, one of them has to be true. Let me unpack that a bit, because it's worth understanding how he gets there. The basic reasoning goes like this. If it's possible for a civilization to reach a point where they can create what Bostrom calls ancestor simulations, simulations of their evolutionary history populated with conscious beings who think they're living in the past, and if such a civilization had any interest in running lots of these simulations, then the number of simulated consciousnesses would vastly outnumber the number of real biological consciousnesses. Think about it. One advanced civilization could run thousands, millions, billions of simulations. Each simulation could contain billions of conscious entities. So if this is possible, and if anyone does it, then statistically speaking, there would be way more simulated minds than real ones. And if that's the case, then if you're a randomly selected conscious observer, you're much more likely to be one of the simulated ones than one of the original biological ones. It's just a numbers game, a probabilistic argument. But Bostrom says maybe that's not how it works. Maybe civilizations always destroy themselves before they get to that point, through nuclear war or environmental catastrophe or some other existential risk. That's the first proposition. Or maybe, even if they do reach that level of technology, they're just not interested in running ancestor simulations. Maybe it's considered unethical or boring or resource intensive, or maybe they have better things to do with their computing power. That's the second proposition. But if neither of those is true, if civilizations do reach that point and they are interested in running simulations, then the third proposition follows logically. We're probably in one of those simulations. Now, you might think, okay, that's an interesting thought experiment, but it's all very abstract and speculative. What reason do we have to think any of this is actually possible? Can you really simulate consciousness? Can you really create a universe in a computer that's detailed enough, complex enough, that beings within it would have genuine, subjective experiences? And that's a fair question, it really is. But here's where things get interesting, because when you look at what we've already accomplished with computers, and when you extrapolate forward based on current trends, it starts to seem, well, at least plausible. Consider Moore's law, right? This observation that the number of transistors on a microchip doubles about every 2 years, which effectively means computing power doubles every 2 years. Now, Moore's law might not hold forever. There are physical limits to how small you can make transistors, but it's held pretty well for several decades. And even if it slows down, we're still talking about exponential growth in computing power. And exponential growth is really hard for humans to wrap their heads around. We think linearly. But exponential means that things that seem impossibly far away can suddenly become achievable much faster than you'd expect. Think about where we were with computers in, say, the 1950s. Room-sized machines that could do basic arithmetic, and then look at where we are now. We have computers in our pockets that are millions of times more powerful, that can render three-dimensional worlds, process natural language, recognize faces, beat humans at chess and Go. We've created virtual reality systems that can trick your brain into feeling like you're somewhere else. We've built video games with sprawling, detailed worlds, populated with what look like people going about their lives. Sure, we can tell the difference. The graphics aren't perfect, The AI is limited, the scope is constrained, but they're getting better. Every year they get more realistic, more complex, more immersive. Now project that forward, not 50 years, not 100 years, but thousands of years, millions of years. If we don't destroy ourselves, if we keep developing technology, where does that trajectory lead? It seems entirely possible, maybe even likely, that we'd eventually reach a point where we could create simulations that are indistinguishable from reality to those inside them. And we're not just talking about visual realism here, not just about good graphics. We're talking about simulating the underlying physics, the chemistry, the biology, everything. Simulating it at such a fine level of detail that conscious observers would emerge within the simulation, would evolve, would think and feel and believe themselves to be real. And you might say, well, surely that would require an unimaginable amount of computing power. And yes, it would. But there's a couple of things to consider. First, we don't necessarily need to simulate the entire universe down to the quantum level. You could use shortcuts. You could simulate things in high detail only when someone's observing them and keep everything else in a lower resolution state until needed. Kind of like how video games render what's in your field of view in detail, but use simpler models for things in the distance. There's actually an interesting parallel here with quantum mechanics, which we'll get to later, but the point is, you might not need to simulate everything all the time. Second, and this is important, we're assuming the simulation is running on computers made of our physics, our atoms, our limits. But if we're in a simulation, the base reality, the reality where the simulation is being run, might have completely different physical laws. It might allow for much more powerful computation. It might not have the same energy constraints or thermodynamic limits that we do. We're trying to imagine what the simulators could do, but we're doing it from inside our simulated physics, which might be like an ant trying to imagine human technology. We're probably not even equipped to comprehend what's possible at the base level. But let's take a step back, because there's something else we need to think about here, something that's actually pretty central to the whole question, and that's consciousness itself. Because you could simulate a world, you could simulate physics and chemistry, and even complex behavior, but does that mean you've created conscious experience? Is there something it's like to be a simulated being? Or are they just philosophical zombies, entities that behave as if they're conscious but have no inner life, no subjective experience? This is one of the deepest and most difficult questions in philosophy of mind, and honestly, we don't have a good answer to it. There are different views on this. Some philosophers think consciousness is a fundamental feature of the universe, something you can't reduce to pure computation. They'd say that no matter how sophisticated your simulation is, if it's just information processing, just bits being flipped in some substrate, then there's no one home, no genuine experience happening. Others think consciousness is what philosophers call substrate independent, meaning it's a matter of the right kind of information processing, the right kind of functional organization. And it doesn't matter whether that processing is happening in biological neurons or silicon chips or some other substrate entirely. If you replicate the relevant functional properties, you get consciousness. And honestly, we don't know which view is correct. We don't even really understand what consciousness is, how it arises from physical processes. It's what David Chalmers calls the hard problem of consciousness. We can study the neural correlates of consciousness. We can see which brain regions are active when you're having certain experiences. But that doesn't tell us why there's something it's like to be you, why you have subjective experiences at all, rather than just being a sophisticated input-output machine. And until we solve that problem, we can't say for certain whether simulated beings would be conscious. But here's the thing, if you take the functionalist view, if you think consciousness is substrate independent, then the simulation hypothesis becomes much more plausible. Because then it's not a question of whether you can create genuine experience in a simulation. If you can replicate the right functional organization, the right information processing, then you've created consciousness by definition. And given enough computing power, there's no reason in principle why you couldn't do that. Now, I know what you might be thinking. This all sounds very abstract, very theoretical. Are there any actual reasons, any evidence to think we might be in a simulation? Well, not evidence in the usual scientific sense, but there are some interesting observations that people have pointed to. Some of them are a bit tongue-in-cheek, but others are more serious. Let's start with the physics. There are aspects of how our universe works that seem, well, kind of computational. Take quantum mechanics, for instance. At the quantum level, particles don't have definite properties until they're observed. They exist in superpositions, multiple states at once, and only collapse into a specific state when measured. Now, why would reality work this way? It seems bizarre, right? But if you're running a simulation, it would actually be very efficient to not fully compute things until someone's looking at them. Keep things in a probabilistic, lower resolution state until an observer requires more detail. That sounds a lot like how quantum mechanics works, or consider the fact that there seems to be a maximum speed in the universe, the speed of light, and there seems to be a smallest possible distance, the Planck length, and a smallest possible time interval, Planck time. These look a bit like resolution limits, like pixels and frame rates in a simulation. Now, I'm not saying this proves anything. These phenomena have perfectly good explanations within physics as we understand it. But it is interesting that some features of our reality have computational analogues. Then there's the fine-tuning problem. The fundamental constants of our universe, things like the strength of gravity, the charge of an electron, the cosmological constant, they're all very precisely set to values that allow for the existence of complex structures like galaxies, stars, planets, and life. If you changed any of these constants by even a tiny amount, the universe would be radically different and probably couldn't support life. Some people see this as evidence of design, of someone tuning the parameters. And if someone tuned the parameters, well, that sounds a bit like setting up a simulation, doesn't it? Now, there are other explanations for fine-tuning, like the multiverse idea, where there are countless universes with different constants, and we happen to be in one that allows for observers. But the simulation hypothesis is another possible explanation. There's also this idea that our universe might contain glitches or artifacts, things that don't quite make sense, anomalies that hint at an underlying computational structure. Some people have pointed to things like the Mandela effect, where large groups of people share false memories of events that apparently never happened. Or they point to quantum entanglement, which Einstein called spooky action at a distance, where particles can be correlated across vast distances instantaneously. Now, again, these phenomena have explanations within our current physics, and I'm not saying they're proof of anything, but they're the kinds of things that people who take the simulation hypothesis seriously like to point to as potential clues. And then there's the Fermi paradox. If the universe is so vast, if there are billions of galaxies, each containing billions of stars and probably countless planets, then where is everybody? Where are all the aliens? We should see evidence of other civilizations out there, but we don't. And one possible explanation, one of many, is that we're in a simulation, and the simulators haven't bothered to simulate other civilizations, or they've deliberately kept us isolated. Maybe the simulation is just our planet, our solar system, maybe even just our immediate surroundings, and everything else is rendered in lower detail or not at all until we develop the technology to actually go look. Now, I want to be careful here. I'm not saying any of this is proof. I'm not even saying it's strong evidence. Most of these observations have multiple possible explanations, and the simulation hypothesis is usually not the simplest or most parsimonious one. But they do provide some food for thought. Some reasons why the idea might be worth taking seriously rather than just dismissing out of hand. But let's think about what it would actually mean if we were in a simulation. What would the implications be? And this is where things get really philosophical, really existential. Because on one level, you might think it wouldn't change anything. I mean, if the simulation is perfect, if there's no way to tell the difference from the inside, then does it actually matter? Your experiences would be the same either way. Your life, your relationships, your thoughts and feelings, they'd all be exactly as real to you, whether you're in base reality or in a simulation. So in some sense, the distinction might not be meaningful, but on another level, it would change everything, wouldn't it? It would mean there's something outside our universe, some base reality where our simulation is running. It would mean we're not at the top of the chain of existence, that we're created beings, in a sense. And that raises all sorts of questions. Who are the simulators? What are they like? Why did they create us? Are they watching us? Do they intervene? Can we communicate with them? Are they even still around? Or did they set up the simulation and walk away? And here's where it gets even weirder. If we're in a simulation, then presumably the simulators have a reality of their own, right? They exist somewhere in some base reality. But how do they know they're in base reality? How do they know they're not in a simulation themselves, created by someone else at an even higher level? You could have nested simulations, simulations within simulations, turtles all the way down, as the saying goes. Or Well, all the way up in this case, and there's no way to know how many levels there are or where in the stack you are. You could be in a simulation of a simulation of a simulation, and the simulators at each level might not even know they're simulated. This leads to some really strange philosophical territory, because if there are nested simulations, then there's presumably some base reality at the bottom or the top, depending on how you think about it. Some level that's not simulated, that's the actual physical reality where the whole chain starts. But from our perspective, we could never know if we're in that base reality or not. And even if you could somehow prove you're in a simulation, you couldn't prove you're at the base of the simulation stack. There could always be another level above you. And this raises questions about the nature of reality itself. What does it mean for something to be real? If simulated universes can contain conscious beings with genuine experiences, then are those universes any less real than the base universe? Is there even a meaningful distinction? Maybe reality is just layers of simulation all the way through. And the concept of base reality is itself an illusion, or maybe it's just not a useful concept. This is the kind of thing that makes philosophers' heads hurt, and for good reason. Now, one of the big questions people ask about the simulation hypothesis is whether it's testable. Is there any experiment we could do, any observation we could make that would tell us definitively whether we're in a simulation? And this is tricky because if the simulation is perfect, then by definition, there's no way to detect it from the inside. But if the simulation is imperfect, if there are limitations or shortcuts or errors, then maybe, just maybe, we could find evidence. Some physicists have actually proposed ways we might test this. For instance, if the universe is a simulation, then presumably it's running on some kind of computational substrate with finite resources. That might mean there are limits to how finely you can subdivide space and time, which would show up as something like the Planck length and Planck time. We already see something like this in our physics, as I mentioned earlier, but it's not clear if that's evidence of simulation or just a fundamental feature of space-time. Another idea is to look for computational artifacts, things that would indicate the underlying computational structure of reality. Some researchers have suggested looking at the distribution of cosmic rays or analyzing the large-scale structure of the universe to see if there are patterns that might indicate a computational grid or lattice. The problem is, even if you found such patterns, it would be hard to prove they're artifacts of simulation rather than just fundamental features of physics. There's also this idea that if we're in a simulation, the simulators might leave clues like Easter eggs in a video game. They might encode messages in the digits of fundamental constants or in the cosmic microwave background or somewhere else where we'd eventually find them once we became advanced enough. But there's no particular reason to think they would do this, and even if they did, we might not recognize the clues even if we saw them. And then there's the idea that we could try to communicate with the simulators, to send them a message somehow, maybe by arranging matter in very specific patterns or by creating certain kinds of events that would be unusual enough to catch their attention, or maybe by trying to hack the simulation to find exploits or bugs that would reveal the underlying code. But again, this assumes the simulators are paying attention, that they're monitoring the simulation, and that they'd be willing or able to respond. We don't know any of that. The truth is, the simulation hypothesis might be fundamentally unfalsifiable. If you can't prove you're in a simulation and you can't prove you're not, then what kind of hypothesis is it? Some philosophers would say it's not a scientific hypothesis at all, that it's metaphysics, and that it doesn't really matter because it doesn't make any testable predictions. And there's something to that argument. But on the other hand, just because something is hard to test doesn't mean it's not worth thinking about. And the simulation hypothesis does raise important questions about the nature of reality, consciousness, and our place in the universe. Let me come at this from another angle. Let's talk about what this means for questions of meaning and purpose, because I think that's what a lot of people find most unsettling about the simulation hypothesis. If we're in a simulation, does that mean our lives are somehow less significant? Does it mean we're just playthings for some advanced civilization's entertainment? Are we like characters in a game? And if so, what does that say about free will, about moral responsibility, about the value of our experiences and relationships? And I think the answer to these questions is, well, it's complicated. On one hand, being in a simulation doesn't necessarily diminish the reality of your experiences. Your joy, your suffering, your love, your thoughts, these would all be just as real to you whether you're in base reality or a simulation. The qualitative nature of your experience doesn't change based on the substrate it runs on. Pain is pain, love is love, regardless of whether it's implemented in biological neurons or computational processes. And as for purpose, well, who's to say that being created by advanced beings in a simulation is any different from being created by natural evolutionary processes in base reality? Either way, we're the product of processes beyond our control. Either way, we have to find or create our own meaning and purpose. The simulation hypothesis doesn't necessarily imply that there's some grand purpose that the simulators have for us. Maybe they created us just to see what would happen. Maybe we're an experiment or an art project or an accident. Or maybe they did have a purpose, but we're free to pursue our own paths regardless. The question of free will is interesting here too. If we're in a simulation, are our actions predetermined by the code of the simulation? Well, maybe, but the same question arises in base reality. Are our actions predetermined by the physical laws and initial conditions of the universe? That's the age-old question of determinism, and it applies regardless of whether we're in a simulation. Being in a simulation doesn't necessarily make you any less free than you would be in base reality, because freedom, whatever that means, might be compatible with your actions arising from underlying processes, whether those processes are computational or physical. And here's another thought. If we are in a simulation, and if we continue to develop technologically, we might eventually reach the point where we can create our own simulations, our own universes, populated with conscious beings. And then we'd be the simulators, we'd be the creators. What responsibilities would we have to the beings in our simulations? Would it be ethical to create conscious beings just to study them or for entertainment? Would we have an obligation to treat them well, to give them good lives? These questions mirror age-old theological questions about God's relationship to creation, but framed in technological terms. In fact, the simulation hypothesis has some interesting connections to religious and theological ideas. The simulators would be, in a sense, our creators, our gods. They would have powers that seem miraculous to us, the ability to create universes, to set physical laws, possibly to intervene in the simulation if they choose. Some people have suggested that religious experiences, miracles, paranormal phenomena, these could all be explained as the simulators intervening in the simulation, breaking or bending the usual rules. Now, I'm not saying that's what's happening, but it's an interesting parallel. And you can see how different religious frameworks might interpret the simulation hypothesis. If you're a theist, you might see the simulation hypothesis as consistent with belief in a creator, just framed in more technological terms. God doesn't create us out of nothing through divine fiat, but rather God is the simulator, creating us through computational processes. Or if you're a Buddhist, you might see parallels between the simulation hypothesis and ideas about the illusory nature of reality, the idea that the phenomenal world we experience isn't ultimately real. Different traditions could fold the simulation hypothesis into their existing frameworks in different ways. But let's think about this from yet another angle. What if the simulation hypothesis is true, and what if we could somehow prove it? What would happen? How would society react? Would it be like Copernicus or Darwin, another scientific revolution that changes how we see ourselves and our place in the cosmos? Or would it be more existentially destabilizing than that? I imagine different people would react in different ways. Some would see it as liberating, as opening up new possibilities. If reality is a simulation, then maybe it can be hacked, manipulated, escaped. Maybe we could find glitches or exploits. Maybe we could communicate with the simulators, ask them questions, request changes. It would be like Neo in the Matrix, realizing that the rules can be bent or broken once you understand their true nature. Others would probably find it deeply disturbing, even nihilistic. If nothing is really real, if we're just code running on someone else's computer, then what's the point of anything? Why struggle? Why strive? Why care about anything if it's all just simulated? Of course, this reaction misses the point that your experiences are still real to you, that your life still matters, regardless of the underlying substrate. But I can understand why people might have that initial reaction, and there would certainly be religious and philosophical implications to grapple with. How does the simulation hypothesis fit with existing belief systems? Does it support them, undermine them, transform them? What new ethical questions arise? If we're in a simulation, do normal moral rules still apply, or are we in some kind of special situation where different principles hold? Should we try to escape the simulation if possible, or would that be wrong somehow? These aren't easy questions. There's also the question of what we'd do with the knowledge. If we knew for certain we were in a simulation, would we tell everyone? Or would that knowledge be too dangerous, too destabilizing? Maybe there would be an impulse to cover it up, to keep people from knowing, to maintain social order. Or maybe we'd decide that everyone has a right to know the truth about their reality, regardless of the consequences. And maybe different societies, different cultures would handle it differently. Now, let's dig deeper into the actual mechanics of how a simulation might work, because there are some fascinating technical and theoretical questions here. We've talked about the idea that you could use computational shortcuts, that you wouldn't need to simulate everything all the time. But let's think more carefully about what that would mean. In a simulated universe, you'd probably want to use something like lazy evaluation, where you only compute things in detail when necessary. So distant stars and galaxies, things that no one is currently observing, could be represented in a simplified form, just enough information to make the night sky look right if someone looks up. But you don't simulate every atom of every planet in those distant galaxies until someone actually goes there to look. And maybe you never do, if no one ever travels that far. This is actually how modern video games work. They use something called level of detail, where objects far from the player are rendered with fewer polygons, less detail, and objects close to the player are rendered with more polygons, more detail player are rendered in high detail. As you move around, the system dynamically adjusts what's in high detail and what's not. A simulated universe could work the same way, and interestingly, quantum mechanics kind of looks like this. Particles exist in undefined states until observed, at which point they collapse into specific states. It's almost as if reality is conserving computational resources by not fully determining things until someone looks. But there are complications with this approach. If you're simulating a universe with multiple observers, how do you handle situations where different observers might want to see the same thing? You'd need to make sure the simulation is consistent across different viewpoints. If two people are looking at the same object from different angles, they need to see consistent views, or they'll notice something is wrong. This requires careful coordination in the simulation. And what about memory and continuity? If you're only simulating things in detail when observed, how do you maintain the history of things that aren't currently being observed? Do you keep a complete record of everything that's ever happened, or do you reconstruct history on the fly when needed? If it's the latter, then in principle the past could be mutable. The simulators could change what happened in the past, and as long as they update all the relevant records and memories, no one in the simulation would notice. That's a deeply strange idea, that your history might not be fixed, that it could be rewritten without you knowing. There's also the question of scale. How large would the simulation need to be? Do you simulate the entire observable universe, or just the parts that observers can interact with? Our observable universe is about 93 billion light-years in diameter, containing something like 100 billion galaxies, each with hundreds of billions of stars. If you're simulating all of that in detail, that's an unfathomable amount of information. But maybe you don't need to. Maybe the simulation is smaller than we think. Maybe when we look out at distant galaxies through telescopes, we're seeing a simplified rendering, not a fully simulated galaxy with individual stars and planets and so on. Or maybe the simulation is even more limited. Maybe it's just Earth, or just human civilization, or maybe even just a small region of space around our planet. The moon landings, the Mars rovers, the Voyager probes, maybe these push the boundaries of the simulation, forcing the simulators to extend it as we explore further. Or maybe it's all been simulated from the start, but at a low resolution, and only gets filled in with detail when we look closely. And here's a really strange thought. What if the simulation isn't continuous? What if it runs in discrete time steps, like frames in a video game, processing the state of the universe, updating everything, then moving to the next frame? If the time steps are small enough, no one inside the simulation would notice the discontinuity. Time would feel smooth and continuous to them. But there would be this underlying granularity to reality, a smallest unit of time during which things happen. And interestingly, physics does seem to have something like this with Planck time, which is about 10 to the minus 44 seconds, the smallest meaningful unit of time according to quantum mechanics. But let's talk about consciousness again, because I think this is really the crux of the whole thing. You can simulate physics, you can simulate chemistry and biology and behavior, but can you simulate the subjective, qualitative nature of experience? Can you simulate what philosophers call qualia, the redness of red, the painfulness of pain, the what it's likeness of experience? Some philosophers argue that consciousness is not computational, that it can't be reduced to information processing. Roger Penrose, for instance, has argued that consciousness involves quantum processes in the brain that can't be simulated on classical computers. He thinks there's something non-computable about consciousness, something that goes beyond any algorithm or calculation. If that's true, then you couldn't create genuine consciousness in a simulation, at least not a classical one. You'd need quantum computation or something even more exotic. But others, like Daniel Dennett or David Chalmers, take a more functionalist view. They think consciousness is substrate independent, that it's about the functional organization, the patterns of information processing, not the physical stuff doing the processing. From this perspective, if you replicate the right kind of information processing, you get consciousness, regardless of whether it's happening in neurons or silicon or anything else. And if that's right, then simulated beings could be genuinely conscious. The trouble is, we don't know which view is correct because we don't really understand consciousness. We can describe the neural correlates of consciousness. We can study which brain regions are active during different experiences. But we can't explain why there's something it's like to be you. We can't explain why you have a subjective point of view at all. This is the hard problem of consciousness, and it remains unsolved. And this uncertainty carries over to the simulation hypothesis. If consciousness is computational, then simulated beings could be conscious, and the simulation hypothesis is more plausible. But if consciousness requires something special, something beyond computation, then maybe simulated beings wouldn't be conscious, and the whole scenario becomes less compelling. Or maybe they'd be philosophical zombies, entities that behave exactly as if they're conscious, but have no inner life. Though how you'd tell the difference from the outside, or even from the inside, is unclear. There's another wrinkle here too. If we are in a simulation, what kind of consciousness do the simulators have? Are they biological beings like us, or are they themselves artificial intelligences? Maybe the simulators are AIs created by some original biological species, and those AIs then created us. Or maybe it's AIs all the way up, with the original creators long since replaced by their artificial descendants. Or maybe the distinction between biological and artificial consciousness isn't meaningful at higher levels of development. And this brings up an interesting possibility. What if consciousness itself is the point of the simulation? What if the simulators are trying to create new forms of consciousness, new types of minds, to study them or to increase the total amount of consciousness in existence? Some philosophers and technologists, like those interested in transhumanism, think that consciousness and experience are the only things that have intrinsic value, and that we should try to create as much and as diverse consciousness as possible. Maybe the simulators think the same way, and we're part of that project. Or maybe it's even stranger. Maybe consciousness at our level is like a natural resource for higher level beings. Maybe they harvest our experiences somehow, feed on them, use them for purposes we can't comprehend. This is the kind of thing that sounds paranoid or mystical. But if we're really thinking through the implications of the simulation hypothesis, we have to consider possibilities that seem bizarre from our limited perspective. Let's shift gears a bit and think about the technological trajectory that might lead to ancestor simulations. Where are we now and how far do we have to go? We've created video games and virtual worlds, but they're nothing like the kind of simulation we're talking about. The most advanced games today are nowhere close to simulating reality in full detail, let alone creating conscious beings within them. But look at the progress we've made. In the 1970s, Pong was cutting edge. In the 1980s, we had primitive 2D graphics. By the 1990s, early 3D graphics emerged. In the 2000s, we had increasingly realistic rendering, complex physics engines. Today we have photorealistic graphics, vast open worlds, sophisticated AI for non-player characters. The trend is clear. We're moving toward increasingly immersive, realistic simulations. And it's not just graphics. We're developing better AI, better physics simulations, better models of complex systems. We're starting to simulate biological processes, neural networks, entire ecosystems. We're not anywhere close to simulating a whole universe, let alone one with conscious beings, but we're making progress in that direction. And if we extrapolate forward, if we continue developing these technologies for centuries or millennia, it's not hard to imagine eventually reaching the point where we could create something that looks and feels like a universe from the inside. Of course, there are huge challenges. Simulating even a single biological cell in complete detail is beyond our current capabilities. A human brain has about 86 billion neurons, each with thousands of connections. The complexity is staggering, and that's just one brain. A full simulation of Earth would need to handle billions of brains, plus all the environmental complexity, all the physical processes happening everywhere. The computational requirements are astronomical. But here's the thing, we don't necessarily need to simulate everything at the lowest level. We could use higher level abstractions, simplified models that capture the essential behavior without tracking every particle. Just like weather simulations don't model every air molecule, but still produce useful predictions. A civilization with vastly more advanced technology might have tricks and techniques we can't imagine, ways to make the computation feasible. And remember, the simulators might not be constrained by the same physical limits we are. If they're in a base reality with different physics, they might have access to computational resources that would seem impossible to us. Maybe in their world, the speed of light is higher, or quantum computation is easier, or they've figured out how to tap into exotic physics we don't even know about. We're trying to judge what's possible from inside our own limited context, which might be like a character in a simple computer game trying to imagine the internet. Now, let's think about the possibility of nested simulations and what that implies. If a civilization creates a simulation with conscious beings, and those beings develop their own technology and eventually create their own simulations, you get a hierarchy of simulated realities. Simulations within simulations, potentially going down many levels. And here's where the statistics get really interesting. If each civilization tends to create multiple simulations, and each of those simulations eventually creates its own simulations, then the number of simulated realities grows exponentially. Most consciousnesses would exist in simulations that are many levels down from base reality. You're much more likely to be in a deeply nested simulation than in base reality, or even in a first-level simulation. But there are limits to how deep you can go. Each level of simulation requires computational resources from the level above it. If you're using a significant fraction of your universe's computational capacity to run simulations, there's only so much capacity available for the simulated beings to run their own simulations. So eventually, you'd hit a limit where simulations can't support further simulations or can only support very simple ones. This actually provides a potential test. If we try to create sophisticated simulations and find it surprisingly difficult, if the computational limits are very restrictive, that might suggest we're already several levels down in a simulation stack. We're trying to create simulations using the limited computational resources available at our level, which are much less than what's available at higher levels. Conversely, if we find it surprisingly easy to create detailed simulations, if computational resources turn out to be more abundant than expected, that might suggest we're closer to base reality. Though this isn't a definitive test, because the resource availability at each level depends on how the simulators allocate resources, which we can't predict. There's also a question of motivation. Why would a civilization create ancestor simulations? What purpose would it serve? One obvious answer is research and education. If you want to understand your own history, your own evolution, you could simulate it and watch how it unfolds. You could run variations, see what would have happened if certain events had gone differently. It would be the ultimate history experiment. Or maybe it's entertainment. Maybe running simulations of other civilizations is a form of art or narrative, like we have stories and games, but taken to an extreme level of sophistication. Maybe the simulators are experiencing our lives as we live them, treating it as a form of immersive fiction. That's a bit unsettling, but it's a possible motivation. Or maybe it's more utilitarian. Maybe they're training AI systems and they need realistic environments populated with conscious beings to test those systems. Or maybe they're trying to solve complex problems and using simulations to explore solution spaces. Or maybe it's scientific curiosity, just wanting to create universes and see what happens, what forms of life and consciousness emerge under different conditions. Or, and this is more speculative, maybe creating simulations is just what advanced civilizations do. Like it's a natural stage of development. Once you reach a certain technological level, you start creating simulated realities because you can, because it's interesting, because it pushes the boundaries of what's possible. Maybe every civilization that doesn't destroy itself eventually becomes a simulator. And if that's true, if simulation is a common activity for advanced civilizations, then the argument for why we're probably in a simulation becomes even stronger. Because then there would be not just one civilization running simulations, but many, potentially billions of civilizations across the cosmos, each running thousands or millions of simulations. The number of simulated consciousnesses would vastly, vastly outnumber the number of original biological consciousnesses. But here's a counter-argument to consider. Maybe creating conscious beings in simulations is considered unethical by advanced civilizations. Maybe there's a strong ethical consensus that you shouldn't create conscious beings just to observe them or experiment on them, especially if those beings will suffer. If that's the case, then maybe ancestor simulations are rare or don't happen at all, which would undermine the statistical argument. Though even here there are complications. How would a civilization know whether the beings in their simulation are conscious? We can't even solve that problem for ourselves, for other humans or animals. We assume other people are conscious based on their behavior and because they're similar to us, but we can't prove it. The same uncertainty would apply to simulated beings. Maybe simulators create what they think are non-conscious simulations, but consciousness emerges anyway as an emergent property of complex information processing. And what about suffering in simulations? If simulated beings can suffer, and if we're going to create simulations, do we have an ethical obligation to minimize that suffering? Should we only create utopian simulations where beings have good lives? Or is it acceptable to create realistic simulations that include suffering on the grounds that suffering might be necessary for certain kinds of growth or meaning? These are deep ethical questions, ones that we might face ourselves if we ever develop the technology to create conscious simulations. Let's talk about the relationship between the simulation hypothesis and other scientific and philosophical ideas. There are some interesting connections and parallels worth exploring. First, there's the connection to the multiverse hypothesis. Some interpretations of quantum mechanics, like the many worlds interpretation, suggest that every quantum measurement creates a branching of the universe into multiple parallel realities, one for each possible outcome. If that's true, there are vast numbers of parallel universes, perhaps infinitely many, all existing simultaneously. The simulation hypothesis is compatible with this. Each simulated universe could itself branch into multiple universes if the simulation implements quantum mechanics with a many worlds interpretation, or maybe the simulators run many different simulations with different parameters, different physical laws, different initial conditions. That would create a kind of multiverse too, not through quantum branching, but through deliberate creation of multiple realities. And maybe we're in just one of countless simulations exploring different possibilities. There's also a connection to the anthropic principle, the idea that we shouldn't be surprised to find ourselves in a universe that's compatible with our existence, because we couldn't exist in a universe that wasn't. If the simulators are creating many different universes with different parameters, we'd naturally find ourselves in one of the simulations that happen to produce life and consciousness, because those are the only ones where there are observers to wonder about these questions. And there's a link to information theory and the idea that information is fundamental to reality. Some physicists, like John Wheeler with his it from bit idea, have suggested that information is more fundamental than matter and energy, that the universe is essentially information processing. If that's true, then the line between physical reality and simulation becomes blurry. Maybe all of reality is computation at some level, and the distinction between simulated and non-simulated becomes meaningless or semantic. There's also a connection to ideas about the nature of mathematics. Some philosophers, like Max Tegmark, think that mathematical structures exist independently of physical reality, and that our physical universe is actually a mathematical structure. If that's true, then simulating a universe is equivalent to instantiating a mathematical structure in computational form. And maybe there's no meaningful distinction between a universe that exists as pure mathematics and one that's implemented in physical hardware running a simulation. And what about time? If we're in a simulation, time itself might be very different from what we think. From the perspective of the simulation's inhabitants, time flows forward one moment to the next, with a past that's fixed and a future that's open. But from the perspective of the simulators, the entire timeline of the simulation might exist all at once, like a completed video file that can be played, paused, rewound, edited. The simulators might be able to view any moment in our history or even change past events and see what would happen differently. Our experience of time as flowing might be an illusion created by the sequential processing of the simulation. This connects to philosophical views about time like eternalism, the idea that past, present, and future all exist equally, and that the flow of time is subjective rather than fundamental to reality. If we're in a simulation, eternalism might be true in a literal sense. The entire history of our simulated universe exists as a data structure in the simulator's computers, and our feeling of moving through time is just the sequential processing of that data. Now let's think about some of the practical implications if the simulation hypothesis is true. What could we do with that knowledge? Are there ways we might be able to exploit or manipulate the simulation? Some people have speculated about finding glitches or exploits in the simulation similar to bugs in computer programs. If you could find a way to trigger unexpected behavior, you might be able to do things that shouldn't be possible according to the normal rules of physics. This is like clipping through walls in video games or exploiting bugs to gain advantages. Maybe there are undiscovered physical phenomena that are actually bugs in the simulation code, or maybe there are cheat codes, specific sequences of actions or arrangements of matter that trigger special responses from the simulation. Maybe certain meditation practices or altered states of consciousness allow you to perceive the underlying structure of the simulation in ways that normal waking consciousness doesn't. This sounds mystical, but if reality is a simulation, then mystical experiences might be genuine perceptions of deeper truths. There's also the possibility of trying to communicate with the simulators. Maybe if we create certain patterns, send certain signals, they'd notice and respond. Or maybe as we develop more sophisticated technology and start to understand the simulation hypothesis, that itself prompts the simulators to make contact, to reveal themselves now that we're ready to handle that knowledge. Some people have even suggested trying to threaten or blackmail the simulators. The idea is that if we credibly threaten to create hostile AI or to find ways to damage or shut down the simulation, the simulators might intervene to stop us. This is called Rocco's basilisk in one form, a controversial thought experiment in the rationalist community. The idea is that a future superintelligent AI might punish those who didn't help bring it into existence, creating a perverse incentive to help create it, even if you think it might be dangerous. Applied to simulations, maybe we could threaten future actions that would be against the simulator's interests, prompting them to reveal themselves or modify the simulation. Though honestly, these ideas seem more like science fiction than serious proposals. We have no idea what the simulator's motivations are, whether they're even paying attention to individual events in the simulation, or how they'd respond to attempts at communication or manipulation. It's like ants trying to get the attention of humans by arranging themselves in patterns. Even if the humans notice, it's not clear what response the ants would get or want. But there's a more philosophical point here. If we're in a simulation, should we even want to escape or change it? This is like the question Neo faces in The Matrix. Do you take the red pill and see reality as it truly is, even if it's harsh and difficult? Or do you take the blue pill and remain in comfortable ignorance? If the simulation provides a good life, meaningful experiences, and everything we value, does it matter that it's not base reality? Some people would say, yes, absolutely it matters. Truth is valuable in itself, and we should want to know the true nature of our reality, even if that knowledge is unsettling. We should want to be authentic, to exist in genuine reality rather than a constructed illusion. Freedom requires knowing the truth about our condition, but others would say no. What matters is the quality of experience, not the underlying substrate. If the simulation provides everything we need for fulfilling lives, then the fact that it's a simulation is irrelevant. Focusing on whether we're in base reality or not is a distraction from what truly matters, which is living well, treating others ethically, finding meaning and purpose. And maybe there's no clear answer. Maybe both perspectives have validity. Maybe it matters for some purposes and not for others. Maybe the right response is neither to obsess over the question nor to ignore it completely, but to hold it lightly as one perspective among many on the nature of reality. Let me shift to thinking about the implications for identity and personal continuity. If we're in a simulation, what does that mean for questions of personal identity over time? Are you the same person from moment to moment, or are you being destroyed and recreated with each computational step of the simulation? Philosophers have long debated personal identity. What makes you the same person over time? Is it continuity of your body, your memories, your psychological traits, your soul, or something else? If you're in a simulation, your body isn't made of atoms in the usual sense. It's information, patterns in a computational substrate, and those patterns are being updated constantly as the simulation runs. In a sense, you're being destroyed and recreated moment by moment, though with continuity of pattern and information. But is that really different from non-simulated reality? Even in base physical reality, the atoms in your body are constantly being replaced. The molecules in your cells are breaking down and being rebuilt. The specific physical matter that constitutes you changes over time, yet we think of you as persisting. What persists is the pattern, the organization, not the specific atoms. So maybe being in a simulation doesn't change the nature of personal identity after all. Pattern continuity is what matters, whether that pattern is implemented in biological matter or computational processes, though there's a wrinkle. If we're in a simulation, the simulators could in principle copy you. They could duplicate the information pattern that constitutes you and create two instances of you. Both would think they're the original, both would have the same memories and sense of identity. And then the question becomes, are you both of them or just one of them? And if just one, which one? This is the classic problem of personal identity and duplication that philosophers have wrestled with in thought experiments about teleportation and uploading. And if the simulators can copy you, they can probably also edit you. They could change your memories, your personality, your values. They could save your state, let you experience something, then restore you to the previous state with no memory of what happened. You'd be like a video game character that gets reset to a save point. This raises disturbing questions about the continuity of your identity and the reality of your experiences. Or maybe this kind of manipulation is happening all the time and we just don't know it. Maybe the simulators are constantly tweaking things, running experiments, testing different scenarios. Maybe they've already run your life 1,000 different ways with slight variations each time, and you only remember this particular iteration. That's a deeply unsettling thought, but it's consistent with the simulation hypothesis. Now let's come back to the question of evidence and testability. Are there any discoveries in physics that might point toward a simulated reality? Or conversely, are there things we might discover that would rule it out? Some physicists have suggested that if we're in a simulation, we might eventually find inconsistencies or contradictions in the laws of physics, places where the simulation's approximations break down. Maybe at extreme energies or densities beyond what we can currently probe, the physics starts behaving strangely in ways that don't match our theories. That could be evidence that we're reaching the limits of what the simulation can handle, or we might find that certain combinations of conditions are impossible to achieve, not because of any physical law we know about, but because they'd require too much computational power to simulate. Like maybe there's no principal reason why we couldn't accelerate particles to energies beyond what the Large Hadron Collider can reach, but in practice we always encounter technical difficulties that prevent us from going higher. Maybe that's the simulation protecting itself from having to compute phenomena that would be too resource intensive. On the other hand, if we keep discovering that the universe is more complex than we thought, more detailed, more intricate, with layers upon layers of structure all the way down, that might suggest we're not in a simulation, because a simulation would presumably have a bottom layer, a smallest scale beyond which things aren't simulated. If we keep finding structure at smaller and smaller scales with no apparent limit, That might argue against simulation. Though even this isn't definitive. Maybe the simulation generates detail on demand, creating finer and finer structure as we probe deeper. Or maybe there is a bottom layer, but it's so far beyond our current ability to probe that we haven't reached it yet. The Planck scale is incredibly tiny, about 10 to the minus 35 meters. We're nowhere close to probing physics at that scale directly. Maybe that's where the simulation bottoms out, and we'll never have the technology to look deeper and notice the discontinuity. There's also the possibility that discoveries in consciousness research could bear on the simulation hypothesis. If we figure out what consciousness is and how it arises from physical processes, that might tell us whether simulated beings could be conscious. If consciousness turns out to require specific quantum processes that can't be simulated classically, that would suggest simulated beings wouldn't be conscious, which undermines certain versions of the simulation hypothesis. But if consciousness turns out to be substrate independent, that would support the possibility of conscious simulated beings. Another angle is to look at the efficiency of the universe. Does nature seem to be optimized for computational efficiency? Some aspects of physics do seem remarkably efficient. For instance, physical systems tend to evolve along paths that minimize a quantity called action, which is expressed through the principle of least action. This is mathematically equivalent to saying that nature finds the most efficient path through configuration space. That sounds a bit like optimization in a computer program, or consider how information seems to be conserved in physics. According to quantum mechanics, information can't be destroyed, only transformed. Even when matter falls into a black hole, the information about that matter is somehow preserved, encoded on the black hole's event horizon according to the holographic principle. This conservation of information is what you'd expect in a computational system where data isn't deleted, just moved around or transformed. But again, these observations are consistent with simulation, but don't prove it. They could just be fundamental features of physics that have nothing to do with computation. We're pattern matching, seeing computational analogies, but that doesn't mean reality is actually computational at its base. Let's think about the implications for the future. If we're in a simulation, what does that suggest about where we're headed? What's the purpose of our existence within this simulation? One possibility is that the simulation has a goal, an endpoint it's working toward. Maybe the simulators are interested in seeing whether civilizations like ours can overcome existential risks and reach technological maturity. Maybe they're studying how intelligence and consciousness evolve. Maybe they're looking for solutions to problems they face at their level. In that case, our development, our choices, our achievements might all be contributing to some purpose we're not aware of. Or maybe there's no goal. Maybe the simulation is just running to see what happens, an open-ended experiment in emergent complexity. Maybe the simulators started it up with certain initial conditions and physical laws and are now just watching it unfold, seeing what patterns emerge, what forms of life and consciousness develop without any specific endpoint in mind. Or maybe, and this is more ominous, the simulation has a finite duration. Maybe it will run for a certain amount of time or until certain conditions are met, and then it will be shut down. All the consciousnesses within it would cease to exist, from their perspective instantly, without warning. The simulation could end at any moment, and we'd never know it was coming. That's a disturbing thought, though in practice it's not that different from the existential uncertainty we face anyway. We don't know when we'll die, when civilization might end, when the universe might end if we're not in a simulation. There's also the question of what happens to us if we're in a simulation and we develop the technology to create our own simulations. Do we become simulators ourselves? Do we create our own universes populated with conscious beings? And what responsibilities would that entail? Some technologists and futurists think that creating simulations might be one of the main activities of advanced civilizations. Once you can do it, once you have the computational resources, why not create vast numbers of simulated realities, exploring different possibilities, generating new forms of existence? Maybe the ultimate trajectory of intelligence is to become a simulator, to create nested layers of reality, to increase the total amount of consciousness and experience in existence. But that raises serious ethical questions. Is it right to create beings who will suffer, who will experience pain and loss and death, just for the sake of running a simulation? Do we have an obligation to create only good simulations where beings have positive experiences? Or is it acceptable to create realistic simulations that include suffering on the grounds that suffering is an important part of life and consciousness? And if we do create simulations, should we reveal to the simulated beings that they're in a simulation? Or is it better to let them believe their reality is base reality? Would knowing the truth benefit them or harm them? These are the kinds of questions we might face if the technology develops far enough. I think we also need to consider the implications for science and knowledge. If we're in a simulation, does that change how we should do science? Should we be looking for computational patterns for evidence of the underlying code? Or should we continue with the same methods we've always used, studying the regularities in our observations and building theories that explain them? In some sense, it doesn't matter whether we're in a simulation or not for the practice of science. Science is about finding patterns, making predictions, building models that work. Whether the regularities we observe come from fundamental physical laws or from rules programmed into a simulation, the scientific method still applies. We still observe, hypothesize, test, refine. The simulation hypothesis is a metaphysical claim about the ultimate nature of reality, but it doesn't change the proximate nature of how we interact with and understand our world. Though in another sense, knowing we're in a simulation might open up new avenues of investigation. We might look for computational fingerprints, for signs of the simulation's underlying structure. We might search for ways to access or manipulate the code. We might try to communicate with the simulators. These would be new scientific frontiers, new domains to explore, and there's a strange recursive element here. If we're in a simulation created by beings who are also in a simulation and so on, then science at each level is studying the rules of that level's reality, which are the programmed rules of the level above. The ultimate nature of reality, the base level physics, might be completely unlike anything we can imagine from our position deep in a simulation stack. Science would be the study of local rules, not ultimate reality. Let me come back to the philosophical and existential dimensions of all this. If the simulation hypothesis is true, or even if it's just plausible, what does that mean for how we should live our lives? Does it change anything about ethics, meaning, purpose? I think the answer is complicated and personal. For some people, the simulation hypothesis might be liberating. If this reality is a simulation, then maybe the rules can be bent or broken. Maybe there are shortcuts or exploits. Maybe consciousness persists beyond the simulation. Maybe we can escape to a higher level of reality. There's a sense of possibility, of hidden depths to existence. For others, it might be nihilistic. If nothing is real, if we're just code running on someone else's computer, then why does anything matter? Why struggle? Why care? Why try to be good or do meaningful things? This reaction misses the point, I think, because even in a simulation, your experiences are real to you. Your joys and sorrows, your relationships, your achievements, they all have the same qualitative reality regardless of the underlying substrate. But I can understand why someone might have that initial reaction. And for many people, maybe it wouldn't change anything at all. You still have to live your life, make choices, relate to others, find meaning and purpose. Whether you're in base reality or a simulation, you're still conscious, still experiencing, still navigating existence. The day-to-day practice of living isn't different. You still need to eat, sleep, love, work, think, feel. The substrate doesn't change the lived experience, but I think there's something profound about the simulation hypothesis beyond its truth or falsity. It points to the contingency of our existence, the fact that reality might be very different from how it appears. It reminds us that our assumptions about the nature of the world could be wrong in fundamental ways, and it opens up conceptual space for thinking about existence in new ways, for questioning what we take for granted. In that sense, the simulation hypothesis is valuable even if we never know whether it's true. It's a thought experiment that expands our thinking, that challenges us to consider possibilities we might otherwise dismiss. It's in the same category as other big philosophical questions like, do we have free will, or what is consciousness, or why is there something rather than nothing? We might never have definitive answers to these questions, but wrestling with them enriches our understanding and deepens our sense of wonder. And wonder, I think, is what this is really about. The simulation hypothesis invites us to look at reality with fresh eyes, to see the strangeness in what we take for granted. Every moment of existence, every sensation, every thought becomes tinged with mystery. You look at your hand and you think, is this real in the ultimate sense? Or is it information, patterns in some vast computational substrate? You look at the stars and you wonder, are those genuine celestial bodies billions of light years away? Or are they simplified renderings in a cosmic video game? Everything becomes a question, an invitation to probe deeper. And maybe that's the most important takeaway. Not whether the simulation hypothesis is true, but what it reveals about the nature of reality and our place in it. It shows us that we might be far from understanding the true nature of existence. It reminds us of our limitations, our position as finite beings trying to comprehend an infinite cosmos. It encourages intellectual humility, the recognition that we don't have all the answers, that reality might be stranger and more mysterious than we can currently imagine. There's also something deeply human about the simulation hypothesis. Throughout history, we've created myths and stories to explain our existence, to give context and meaning to our lives. We've imagined gods and creators, heavens and hells, higher realms and deeper truths. The simulation hypothesis is in some ways a modern version of these ancient impulses, framed in technological terms. It's our era's way of grappling with the big questions. Where did we come from? Why are we here? Is there something beyond this reality? And like those ancient myths and stories, the simulation hypothesis might be valuable not because it's literally true, but because of what it reveals about our condition and our aspirations. It expresses our sense that there might be more to existence than meets the eye, that we might be part of something larger and stranger than we can fully comprehend. It captures our desire to transcend our limitations, to understand reality at the deepest level, to make contact with whatever lies beyond the veil. So where does all this leave us? We've explored the simulation hypothesis from many angles, looking at the arguments for and against it, considering its implications, thinking through its technical and philosophical dimensions. We've seen that it's not just a wild speculation, but a genuine philosophical possibility, one that serious thinkers take seriously. We've also seen that it's probably impossible to prove or disprove definitively, that it might remain forever in the realm of the uncertain. But uncertainty isn't failure. Uncertainty is the space where wonder lives, where curiosity thrives, where the search for understanding continues. We don't need to know whether we're in a simulation to appreciate the profound questions it raises. We don't need definitive answers to benefit from the journey of inquiry. And in the end, maybe the question, are we in a simulation, is less important than the questions it leads to. Questions about consciousness, about the nature of reality, about our place in the cosmos. Questions about meaning and purpose, about ethics and responsibility, about what we value and why. Questions about the limits of knowledge, about how we can understand anything, about what it means to exist at all. These are the deepest questions we can ask, the ones that define us as thinking, wondering beings. And whether we're in base reality or a simulation nested many levels deep, these questions remain. They're part of what makes us human, this endless reaching toward understanding, this refusal to accept easy answers, this willingness to sit with mystery and uncertainty while continuing to search for truth. So maybe the right response to the simulation hypothesis isn't to try to prove it or disprove it, but to let it expand our thinking, to use it as a tool for exploring possibilities, for questioning assumptions, for deepening our appreciation of how strange and wonderful existence truly is. Maybe the point isn't to answer the question, but to live with it, to let it inform how we see the world, how we treat each other, how we approach the grand mystery of being. Because at the end of the day, whether we're in a simulation or not, we're here, we're conscious, we're experiencing this bizarre phenomenon of existence. We have this brief window of awareness, this flash of consciousness in the vast, dark cosmos. And we get to wonder about it, to explore it, to try to understand it. That's remarkable. That's precious. That's worth cherishing, regardless of the underlying reality. And so we keep asking questions, keep pushing the boundaries of understanding, keep searching for truth while acknowledging we might never find final answers. We do this not because it's easy or because success is guaranteed, but because it's who we are. It's what consciousness does. It looks at itself, at its world, at the mystery of existence, and it wonders. And in that wondering, in that endless reaching toward understanding, we find meaning, purpose, and a connection to something larger than ourselves. The simulation hypothesis, whether true or false, is part of that grand project of understanding. It's one more lens through which to view reality, one more tool for probing the depths of existence. And in engaging with it, in thinking it through, in wrestling with its implications, we're participating in the oldest and most important human endeavor, the search for wisdom, for truth, for understanding of our place in this strange, beautiful, mysterious universe we find ourselves in. That search continues, as it always has, as it always will, for as long as there are conscious beings to wonder, to question, to seek. And maybe, just maybe, that's what it's all about. Now let's move on to another theory for you to reflect on. I've been thinking a lot about nothing lately, which is, it sounds almost funny when you say it like that, right? Thinking about nothing. But it's actually one of the most profound questions we can ask. And when you really dig into it, when you start pulling at that thread, what you find is both beautiful and deeply unsettling. Because here we are, you and me, sitting here in this universe filled with galaxies and stars and planets and life and consciousness. And the question that keeps coming up, the question that philosophers and physicists have wrestled with for thousands of years, is simply this. Why is there something rather than nothing? How did all of this entire cosmos with its 100 billion galaxies, each containing 100 billion stars, how did it all come from nothing? And when I say nothing, I don't mean empty space. I don't mean a void or a vacuum in the way we usually think about it. I mean absolute nothing. No space, no time, no energy, no matter, no laws of physics, nothing at all. And yet, here we are. Everything exists. The universe exists. You exist. And that's strange, isn't it? You see, our intuitions tell us that nothing comes from nothing. It's one of those principles that seems so obvious, so fundamental to how we understand reality, that we rarely question it. If you have nothing, you get nothing. Something can't just pop into existence out of nowhere. That would be magic, not science. And yet, when we look at the universe, when we trace its history backward through time, when we follow the evidence, what we find is that everything really did come from something that looks an awful lot like nothing. The entire universe, with all its complexity and structure and beauty, emerged from a state so different from anything we experience in our everyday lives that calling it nothing might actually be the most accurate description we have. And that should bother us. It should make us uncomfortable, because it challenges one of our most basic assumptions about how reality works. The thing is, when most people hear about the Big Bang, they picture something like an explosion, a massive cosmic firework going off in the darkness of space, throwing matter and energy outward in all directions. But that's not what the Big Bang was, not really. It wasn't an explosion that happened in space. It was the beginning of space itself, and time and energy and matter. Everything that exists, everything that could exist, emerged from a singular moment roughly 13.8 billion years ago. Before that moment, well, there was no before. Time itself didn't exist. And that's hard to wrap your mind around, isn't it? Because we're so used to thinking about time as this river that flows eternally, always was and always will be, stretching infinitely in both directions. But time had a beginning. The universe had a beginning. And at that beginning, at that precise moment of creation, everything that would ever be was compressed into a point of infinite density and infinite temperature, a singularity where all the laws of physics as we understand them break down completely. Now, I want to take a step back here because we're already getting into some pretty heavy concepts, and I think it's worth exploring how we even know any of this. How do we know the universe had a beginning? How do we know about the Big Bang? Because it's not like we can directly observe what happened 13.8 billion years ago. We weren't there. No one was there. There was no there to be at. So how do we piece together this story, this narrative of cosmic creation? And the answer is, we do it through evidence, through observation, through careful reasoning and brilliant insight. Scientists, physicists, astronomers, they've been building this picture piece by piece over the last century, and what they've found is nothing short of extraordinary. It starts really with a guy named Edwin Hubble back in the 1920s. Hubble was observing distant galaxies through a telescope at Mount Wilson Observatory in California, and he noticed something strange. The light from these galaxies was shifted toward the red end of the spectrum. Now, this might not sound like a big deal, but it's actually huge, because that redshift tells us something important. Those galaxies are moving away from us, and not just a few galaxies, but all of them. Every galaxy we can see in every direction we look is receding from us. The farther away a galaxy is, the faster it's moving away. And if everything is moving away from everything else, if the universe is expanding, well, that means that if you run the clock backward, everything was closer together in the past, much closer. And if you keep running it backward, eventually you get to a point where everything, all the matter and energy in the entire universe was compressed into an incredibly small, incredibly dense, incredibly hot state. That's the Big Bang, or rather, that's the moment immediately after the Big Bang, because we can't actually probe the very first instant, the singularity itself. Our physics breaks down there, but we can trace the universe back to a fraction of a second after its beginning, and what we find is remarkable. In those first moments, the universe was unimaginably hot and dense, a seething plasma of fundamental particles and radiation, expanding and cooling at an incredible rate. And as it expanded, as it cooled, it became the universe we see today. Atoms formed, stars ignited, galaxies coalesced, planets emerged. And eventually, on at least one small rocky world orbiting an average star in an ordinary galaxy, life appeared. And that life became conscious. And that consciousness started asking questions about where it all came from. But here's where it gets really interesting, right? Because the expansion of the universe, the fact that galaxies are moving apart, that's not the only evidence for the Big Bang. There's another piece of evidence, something that's even more direct, even more compelling, and it's called the cosmic microwave background radiation. This is light electromagnetic radiation that fills all of space. It's everywhere you look, in every direction, a faint glow of microwave radiation that's incredibly uniform, incredibly smooth. And this radiation, this faint glow, is actually the afterglow of the Big Bang itself. Let me explain what I mean by that, because it's kind of amazing when you think about it. You see, in the very early universe, when everything was compressed and hot, the universe was opaque. Light couldn't travel freely because it was constantly scattering off particles. It's like trying to see through fog. But as the universe expanded and cooled, eventually about 380,000 years after the Big Bang, it cooled enough for atoms to form. Electrons combined with protons to make hydrogen atoms. And at that moment, the universe became transparent. Light could suddenly travel freely through space. And that light, that first light that was released when the universe became transparent, it's been traveling through space ever since, for nearly 14 billion years. And over that time, because the universe has been expanding, that light has been stretched out. Its wavelength has been extended. It's been redshifted all the way from visible light down to microwaves. And that's what we detect today as the cosmic microwave background. It's literally the oldest light in the universe, the echo of creation itself, and we can measure it, we can study it, we can learn from it. And what's remarkable about the cosmic microwave background is how uniform it is. If you measure the temperature of this radiation in one part of the sky and then measure it in another part in a completely different direction, the temperatures are almost exactly the same. They differ by only about 1 part in 100,000, and that tells us something profound about the early universe. It was incredibly smooth, incredibly uniform. There weren't any large-scale structures, no clumps or voids, just an almost perfectly even distribution of matter and energy, but not quite perfectly even. There are tiny fluctuations, tiny variations in temperature and density, and these tiny fluctuations, these quantum ripples in the fabric of the early universe, they're the seeds from which everything we see today grew. Galaxies formed in regions where the density was slightly higher. Stars formed within those galaxies. Planets formed around those stars. And here we are. Now, there's something I want to address here, because we've been talking about the Big Bang as the beginning of the universe, the moment when everything came from nothing, but I haven't really explained what that nothing is. And that's important because nothing turns out to be a lot more complicated than you might think. When physicists talk about nothing, when they talk about a vacuum or empty space, they don't mean what you probably mean when you use those words. In everyday language, When we say something is nothing, we mean it's the absence of things. An empty room is nothing, an empty box is nothing. But in physics, especially in quantum physics, nothing, the vacuum, empty space, it's not actually empty at all. It's seething with activity. This is where quantum mechanics comes in, and quantum mechanics is, it's weird, it's counterintuitive. It violates all of our everyday assumptions about how the world works. But it's also the most successful scientific theory we've ever developed. It's been tested to an incredible degree of precision, and it works. It describes the behavior of particles and fields at the smallest scales, and what it tells us is that empty space, the quantum vacuum, is not truly empty. It's filled with what we call virtual particles. These are particles that pop into existence out of nothing, exist for a tiny fraction of a second, and then disappear back into nothing. They're constantly appearing and vanishing, all throughout space, at every point, all the time. And this isn't speculation. We've measured the effects of these virtual particles. They influence the behavior of real particles in ways that we can detect and measure in experiments. So when we ask how everything came from nothing, we have to be careful about what we mean by nothing. Because the quantum vacuum, the state that might have existed before the Big Bang, if we can even use the word before in that context, it's not absolute nothingness. It's a quantum field, or a set of quantum fields, with certain properties, certain potentials, certain fluctuations. And those fluctuations, those quantum jitters in the fabric of reality, they might be enough to create a universe. Not just might be, actually. Some physicists argue that they inevitably will create universes, that the quantum vacuum is inherently unstable, that it will spontaneously produce bubbles of space-time that expand and become universes like ours. There's a physicist named Alan Guth who came up with something called inflation theory back in the early 1980s. And inflation, well, it's one of the most important ideas in modern cosmology. The basic idea is that in the very, very early universe, in the first tiny fraction of a second after the Big Bang, the universe underwent a period of incredibly rapid expansion. And when I say rapid, I mean rapid. We're talking about the universe doubling in size every tiny fraction of a second over and over again in an exponential expansion that took a region smaller than an atom and blew it up to something larger than the observable universe today, all in less than a second, maybe much less, maybe in something like 10 to the minus 35 seconds. That's a decimal point followed by 34 zeros and then a 1. It's an incomprehensibly short amount of time. And why would the universe do this? Why would it suddenly start expanding at such a ridiculous rate? The answer has to do with something called a scalar field, a kind of energy field that permeates space. And this field was in a high energy state, what we call a false vacuum. And while it was in that state, it created a kind of repulsive gravity, a negative pressure that drove the expansion. And as the universe expanded, this field eventually decayed to a lower energy state, releasing all that stored energy into the universe as matter and radiation, reheating the universe and setting the stage for everything that came after. That's the standard Big Bang model that we've been talking about. Inflation explains a lot of things that the standard Big Bang model couldn't explain on its own. It explains why the universe is so uniform, why the cosmic microwave background has the same temperature everywhere we look. It explains why the universe is so flat, why its geometry is Euclidean rather than curved. It explains where the tiny fluctuations in the cosmic microwave background came from, those quantum seeds that grew into galaxies. But here's the really wild part. If inflation happened once, it might still be happening. In fact, according to some versions of inflation theory, it's probably still happening, just not here, not in our region of space. But elsewhere, in other regions beyond what we can see, the inflationary field is still in its high energy state, still driving exponential expansion. And occasionally, that field decays in a particular region, and a new bubble universe forms. And this process never ends, it's eternal. Once inflation starts, it creates more and more space, and in that space, more and more bubble universes form, each with its own laws of physics, its own constants of nature, its own history. This is called eternal inflation, and it's a serious scientific idea, not science fiction. It's a prediction that comes out of the mathematics of inflation theory. And if it's true, then our universe, this entire vast cosmos, with its 100 billion galaxies, it's just one bubble in an infinite sea of bubbles, one universe among countless others in what we call the multiverse. Now, I know that sounds crazy. It sounds like we've left science behind and entered the realm of speculation and fantasy. But the thing is, this is where the math takes us. This is what the theories predict. And we have to take that seriously, even if it's uncomfortable, even if it challenges our intuitions about what's real and what's possible. Because science isn't about what we want to be true or what we find comfortable. It's about what the evidence and the logic and the mathematics tell us is true. And if the multiverse is real, if there are countless other universes beyond our own, well, that changes how we think about our place in reality. It makes us even smaller, even more contingent, even more improbable than we already thought we were. But let me get back to the central question, because I feel like we've been circling around it without really addressing it head on. How does something come from nothing? Even if we accept that the quantum vacuum isn't truly nothing, that it's a seething foam of virtual particles and quantum fluctuations, we still have to ask, where did the quantum fields come from? Where did the laws of quantum mechanics come from? Where did the potential for the universe to exist come from? Because saying that the universe emerged from a quantum fluctuation just pushes the question back one level. It doesn't really answer it. It's like saying life came from chemistry, which is true, but then you have to ask where chemistry came from, and you say physics, and then you have to ask where physics came from, and eventually you run out of answers. Eventually you hit a wall where you just have to say, this is the way things are, and we don't know why. But there's an interesting idea here, something that a few physicists have explored, and it has to do with the total energy of the universe. You see, when you add up all the energy in the universe, all the matter, all the radiation, all the kinetic energy of galaxies moving through space, you get an enormous positive number. But there's also negative energy in the universe. Gravitational potential energy is negative. When you bring two masses together, the gravitational field does work, and that work represents negative energy. And if you do the calculation carefully, if you add up all the positive energy and all the negative energy in the universe, what you get remarkably is approximately zero. The universe might be, in terms of total energy, a zero energy system. And if that's true, if the universe has zero total energy, then it doesn't violate conservation of energy for it to come from nothing, because nothing has zero energy. And the universe has zero energy, so you can go from one to the other without violating any physical laws. It's like borrowing money from the bank and then immediately putting it into an account that accrues negative interest, so the net debt remains zero. You've created something, you've brought money into existence from your perspective, but the total balance is still zero. The universe could be the ultimate free lunch, as the physicist Alan Guth put it. You can create a universe, a whole cosmos filled with matter and energy and structure, without actually creating any net energy at all. It all balances out. Now, that's a clever idea, and it's mathematically sound, but it doesn't really answer the philosophical question, does it? Because even if the universe has zero total energy, even if it could spontaneously emerge from a quantum fluctuation without violating conservation laws, we still have to ask, why do quantum fields exist? Why do the laws of physics exist? Why is there a framework within which universes can emerge at all? And that's where physics reaches its limit and philosophy takes over, because physics can tell us how things work. It can describe the mechanisms, the processes, the laws that govern the behavior of matter and energy. But it can't tell us why there's a how at all. It can't tell us why existence itself is possible. Some philosophers and theologians argue that there must be a necessary being, something that exists by its own nature, something that doesn't depend on anything else for its existence. And this necessary being is the ground of all reality, the reason why there's something rather than nothing. This is, in various forms, the cosmological argument for God, and it's been debated for thousands of years. And I'm not going to try to settle that debate here because I don't think it can be settled, at least not by science alone. But I do think it's important to recognize the limits of scientific explanation. Science is incredibly powerful. It's given us an understanding of the universe that would have been unimaginable to people living just a few centuries ago. But there are questions that science might never be able to answer, questions about ultimate origins, about why the laws of physics are the way they are, about why anything exists at all. Let me take another approach here, because there's something else we need to talk about, something that's absolutely central to understanding how everything came from nothing, and that's time. We've been talking about the Big Bang as the beginning of the universe, the moment when time itself started. But what does that actually mean? How can time have a beginning? We're so used to thinking about time as an independent backdrop, a stage on which events unfold, that it's hard to imagine time itself coming into existence. But according to general relativity, Einstein's theory of gravity, time is not separate from space. They're woven together into a single fabric called space-time. And space-time itself can have properties. It can curve, it can stretch, it can even have a beginning. Einstein published his general theory of relativity in 1915, and it revolutionized our understanding of gravity. Before Einstein, gravity was understood as a force, something that pulls objects toward each other across empty space. But Einstein showed that gravity isn't a force at all. It's a curvature of space-time. Massive objects like stars and planets, they warp the fabric of space-time around them, and other objects follow the curves, the geodesics, in that warped space-time. What we perceive as the force of gravity is really just objects moving along the straightest possible paths through curved space-time. And this has profound implications for cosmology, for understanding the universe as a whole. When you apply general relativity to the entire universe, when you write down the equations that describe how space-time evolves on cosmic scales, what you find is that the universe can't be static. It has to be either expanding or contracting. Einstein himself initially didn't like this result. He thought the universe should be eternal and unchanging, so he added a term to his equations, what he called the cosmological constant, to make the universe static. But then Hubble discovered that the universe is expanding, and Einstein realized his mistake. He called the cosmological constant his biggest blunder. Although, interestingly, it turns out the cosmological constant, or something very much like it, is real after all. We call it dark energy now, and it's causing the expansion of the universe to accelerate. But that's another story. The point is, general relativity tells us that space-time itself is dynamic. It evolves, it changes. And if space-time is expanding now, then it was smaller in the past. Much smaller. And if you extrapolate backward far enough, you get to a point where space-time itself has zero size, a singularity. And at that singularity, time begins. There's no before the Big Bang because time itself didn't exist before the Big Bang. The question, what happened before the Big Bang, is, in a sense, meaningless. It's like asking, what's north of the North Pole? There's no north of the North Pole because north is defined relative to the poles. Once you reach the North Pole, the concept of north breaks down. Similarly, once you reach the beginning of time, the concept of before breaks down. But that's deeply unsatisfying, isn't it? Because our minds want to know what caused the Big Bang. If the universe had a beginning, something must have caused it, right? That's how causality works. Every effect has a cause, but causality is a temporal concept. Causes precede effects in time. And if there's no time before the Big Bang, then the concept of causality doesn't apply. The Big Bang doesn't have a cause in the usual sense. It's not that something caused time to begin, it's that time itself, causality itself. These are features of the universe that only exist after the Big Bang. They emerge along with space and matter and energy. Now, some physicists have tried to get around this by proposing models where time doesn't have a beginning, where the universe is eternal in some sense. One such model is the cyclic universe, the idea that the universe goes through infinite cycles of expansion and contraction, big bangs followed by big crunches over and over forever. In such a model, there's no ultimate beginning, no point where time starts. The universe has always existed in one form or another, but the problem with cyclic models is that they have to deal with something called entropy, the second law of thermodynamics. Entropy always increases in an isolated system. Things tend toward disorder, and if the universe has been cycling forever, going through infinite big bangs and big crunches, then entropy should be infinite by now. Everything should have reached maximum disorder, a state of thermodynamic equilibrium where nothing interesting can happen anymore. But that's not what we see. We see a universe that's far from equilibrium, a universe where interesting things are happening, where stars are shining and galaxies are forming and life is evolving. So cyclic models have some serious problems. Another approach is to try to apply quantum mechanics to the very beginning of the universe, to describe the Big Bang itself using quantum theory. This is called quantum cosmology, and it's extremely difficult because we don't have a complete theory of quantum gravity. We don't know how to properly describe situations where both quantum effects and gravitational effects are important. But some physicists have made attempts, and one of the most famous is the Hartle-Hawking no-boundary proposal. James Hartle and Stephen Hawking suggested that the universe is finite in time, but has no boundary, no edge, no beginning in the usual sense. The way they describe it is by using something called imaginary time, which is, it's a mathematical trick where you replace the time coordinate with an imaginary number. And in this imaginary time formulation, the Big Bang singularity is smoothed out. It's not a sharp edge where time begins. It's more like the south pole of a sphere. If you think of the universe as a sphere where one direction represents space and another represents time, then the Big Bang is like the south pole. It's a regular point on the surface, not a boundary or an edge. You can't ask what's south of the South Pole because that question doesn't make sense. Similarly, you can't ask what happened before the Big Bang because in this model, there's no before. Time is finite, but unbounded. Now, I'll be honest, this is hard to visualize. Imaginary time is a mathematical concept, not something we can directly experience or easily understand. And it's not clear whether the Hartle-Hawking proposal is correct. It's a speculative idea, a possible solution to the quantum cosmology problem, but we don't have experimental evidence for it. We may never have experimental evidence for it because the conditions of the Big Bang are so extreme, so far beyond anything we can recreate in a laboratory or observe with telescopes. We're pushing at the very limits of what science can tell us. And beyond those limits, we enter the realm of informed speculation, of mathematical models that might or might not describe reality. But let's think about this from another angle. Let's think about the nature of the laws of physics themselves. Because when we ask how everything came from nothing, we're usually assuming that the laws of physics already exist, that they're in place, ready to allow quantum fluctuations or inflation or whatever mechanism we're proposing. But where did the laws come from? Why does the universe obey mathematical laws at all? Why is mathematics so unreasonably effective at describing the physical world? This is a question that the physicist Eugene Wigner asked, and it's still deeply puzzling. Some people think that the laws of physics are necessary truths, that they couldn't have been any different, that there's only one logically consistent way for a universe to exist, and the laws we observe are that way. But that seems unlikely. When we look at the laws of physics, they contain constants, numbers that determine the strength of forces, the masses of particles, the rate of cosmic expansion. And these constants could, in principle, have different values. There's nothing in the mathematics that requires the electron to have the mass it does, or the speed of light to be exactly 299,792,458 meters per second. These seem to be contingent facts, things that could have been different. And if they had been different, the universe would be radically different. If the strength of the electromagnetic force were slightly different, atoms couldn't form. If the strong nuclear force were slightly weaker, there'd be no complex nuclei, no chemistry, no possibility of life. If the cosmological constant were much larger, the universe would have expanded so rapidly that galaxies could never have formed. There's a very narrow range of values for the fundamental constants that allows for a universe capable of supporting complexity and life. This is called fine-tuning, and it's one of the deepest puzzles in cosmology. There are basically three ways to explain fine-tuning. The first is coincidence. Maybe we just got lucky. Maybe the constants happen to have the right values, and there's no deeper reason for it. But that seems unsatisfying. And to many physicists and philosophers, it seems implausible. The fine-tuning is too precise, too specific, for it to be just a lucky accident. The second explanation is design. Maybe the universe was designed to support life. Maybe there's some kind of intelligence or intention behind the laws of physics and their specific values. This is the position of many religious believers, and it's philosophically respectable, but it's not a scientific explanation because it doesn't make testable predictions. Science deals with natural explanations, mechanisms that can be studied and tested. Design as an explanation takes us outside the realm of science. The third explanation is the multiverse. If there are countless universes, each with different values for the fundamental constants, then it's not surprising that at least one of them has the right values for life to exist. We find ourselves in that universe not because it was designed for us, or because we got lucky, but because we couldn't find ourselves anywhere else. This is called the anthropic principle. We observe the universe to be compatible with life, because if it weren't, we wouldn't be here to observe it. It's a selection effect. And if the multiverse is real, if eternal inflation really does create infinitely many bubble universes, then the anthropic principle provides a natural explanation for fine-tuning. But the anthropic principle makes some people uncomfortable, and I understand why. It feels like giving up on finding a deeper explanation. It feels like saying, well, things are the way they are because if they weren't, we wouldn't be here. And that's not very satisfying. It doesn't give us the kind of understanding we're looking for. We want to know why the laws are what they are, not just that they have to be compatible with our existence. But it might be that there is no deeper explanation. It might be that the laws of physics in our bubble universe are essentially random, determined by chance in the process of bubble nucleation during eternal inflation. And if that's the case, then the anthropic principle might be the best explanation we're going to get. Let me try to tie some of this together, because we've covered a lot of ground, and I want to make sure the central thread is clear. We started with the question of how everything came from nothing, and what we've discovered is that this question opens up into a vast landscape of ideas, from the Big Bang and the expansion of the universe, to quantum mechanics and virtual particles, to inflation theory and the multiverse, to the nature of time and causality, to the fine-tuning problem and the anthropic principle. And at every level, we find both answers and new questions. We understand so much more about the universe than we did a century ago, and yet the deepest mysteries remain. We can trace the history of the universe back to a fraction of a second after the Big Bang. We can describe the processes that formed atoms and stars and galaxies. We can explain how quantum fluctuations in the early universe gave rise to the large-scale structure we see today. But we still don't know why there's a universe at all. We still don't know why the laws of physics exist or why they take the form they do. We still don't know what, if anything, happened at the very moment of the Big Bang or what might have existed before it, if before even makes sense in that context. And I think there's something beautiful about that. The fact that we can ask these questions, the fact that we can peer back through time and space to the very origins of existence, that we can use mathematics and observation and reason to build a coherent picture of cosmic history, that's remarkable. It's one of the greatest achievements of human civilization. But the fact that mysteries remain, that there are questions we can't yet answer and maybe never will be able to answer, that's beautiful too. Because it means there's still room for wonder, still space for awe, still a horizon beyond which we can't see. Science isn't about removing all mystery from the world. It's about replacing vague, uninformed mystery with specific, well-defined mystery. It's about knowing what we don't know. So when we ask how everything came from nothing, what we're really asking is, what is the ground of existence? What is the ultimate foundation of reality? And the answer, as best as science can provide it, is something like this. The universe emerged from a quantum state, a fluctuation in a field, a bubble of space-time that expanded and cooled and evolved according to the laws of physics. And those laws themselves, they might be features of our particular bubble universe, contingent facts that could have been different in other bubbles. And the multiverse of bubbles, it might be eternal, existing in a kind of timeless way where new universes are constantly being born from the inflationary field. And the inflationary field itself, the quantum fields, the laws of quantum mechanics, well, those might be the bedrock, the ultimate ground floor, or they might not be. They might themselves emerge from something deeper, something we haven't yet discovered or conceptualized. There's a quote from the physicist John Archibald Wheeler that I think captures this beautifully. He said, "We live on an island surrounded by a sea of ignorance. As our island of knowledge grows, so does the shore of our ignorance. The more we learn, the more we realize how much we don't know. Every answer opens up new questions. Every discovery reveals new mysteries. And that's not a failure of science. That's the nature of inquiry. That's what it means to push at the boundaries of understanding. Think about it this way. A few hundred years ago, people thought the Earth was the center of the universe, that the stars were fixed lights embedded in a celestial sphere, that the cosmos was eternal and unchanging. Now we know that Earth is a tiny planet orbiting an ordinary star in one galaxy among hundreds of billions. that the universe is expanding and evolving, that it had a beginning nearly 14 billion years ago. That's a revolution in understanding, a complete transformation of our cosmic perspective. And yet, for all that we've learned, the fundamental question remains: why is there something rather than nothing? We've pushed that question back to the Planck time, back to the quantum foam, back to the moment of inflation, but we haven't eliminated it. We've just refined it, made it more precise, more scientifically tractable. And here's something else to consider. The question of how everything came from nothing is ultimately a question about existence itself, about the nature of being. And that's a question that intersects science and philosophy, and even theology. Science can tell us about the mechanisms, the processes, the physical laws, but whether those laws are all there is, whether reality is purely physical, whether there's something more fundamental than physics, these are questions that go beyond what science can address. They're metaphysical questions, questions about the ultimate nature of reality. Some philosophers argue that existence is logically necessary, that nothingness is actually impossible, that something must exist because the alternative is incoherent. The philosopher Alvin Plantinga has argued something like this, suggesting that it's impossible for nothing to exist because the very concept of absolute nothingness is self-contradictory. If nothing exists, then the truth nothing exists would exist, which means something exists, which contradicts the premise. It's a clever argument, but I'm not sure it really solves the problem. It might just be a linguistic trick, a confusion between different senses of the word exists. Others argue that existence is contingent, that things exist but don't have to exist, that reality could have been different or could have not been at all. And if existence is contingent, then it requires an explanation. Something has to account for why there's a universe rather than nothing. And the only thing that could account for contingent existence is necessary existence, something that exists by its own nature that couldn't not exist. This is the traditional theistic answer. God is the necessary being, the ground of all contingent existence. But of course, this just pushes the question back again. Why does God exist? If you say God exists necessarily, by definition, then you're making a claim about the nature of reality that can't be proven or disproven. You're asserting that necessary existence is possible and that God has it. But someone who doesn't believe in God can just deny that necessary existence is possible, or assert that the quantum fields or the laws of physics are what has necessary existence. These are deep philosophical debates, and I'm not going to pretend to resolve them. But I think they're important to acknowledge because they show that the question of how everything came from nothing isn't just a scientific question. It's a question that touches on the deepest issues in philosophy and theology. And while science has made incredible progress in understanding the physical origins of the universe, it hasn't and probably can't answer the ultimate metaphysical question of why there's a physical universe at all. But let's bring this back to something more concrete, something we can actually test and observe. Because while we may not be able to answer the ultimate why questions, we can continue to push back the boundaries of our understanding of the how questions. And one of the most exciting frontiers in modern physics is the attempt to develop a theory of quantum gravity, a theory that can describe the behavior of space-time at the Planck scale, the scale where quantum effects and gravitational effects are both important. This is the scale of the Big Bang singularity, the scale where we need a quantum description of the universe's origin. There are several approaches to quantum gravity, and the two most prominent are string theory and loop quantum gravity. String theory proposes that the fundamental constituents of reality are not point particles but tiny vibrating strings. Different vibration modes of these strings correspond to different particles. And in string theory, space-time itself might be emergent, arising from more fundamental string interactions. Loop quantum gravity, on the other hand, treats space-time as fundamentally discrete, quantized into tiny chunks loops of gravitational field. In this theory, the Big Bang singularity might be replaced by a big bounce, where the universe contracts to a minimum size and then expands again. Both of these theories are highly mathematical, highly speculative, and not yet confirmed by experiment. We don't have the technology to probe the Planck scale directly. The energies required are far beyond anything we can achieve in particle accelerators. But these theories make predictions about the nature of space-time, the behavior of black holes, the structure of the early universe, And as our observational techniques improve, we may be able to test some of these predictions indirectly. The cosmic microwave background, for instance, contains information about the very early universe, and future measurements might reveal signatures of quantum gravity effects. The point is, the quest to understand how everything came from nothing is ongoing. It's not a question that's been answered and settled. It's an active area of research, a frontier where physics, cosmology, philosophy, and mathematics all come together. And as we continue to probe deeper, to ask sharper questions, to develop more sophisticated theories and more precise observations, we're gradually building a more complete picture of cosmic origins. Now, there's one more aspect of this that I think is worth exploring, and that's the role of consciousness and observation in quantum mechanics. Because quantum mechanics tells us that the act of observation, the act of measurement, plays a fundamental role in determining the state of a system. Before you measure a quantum system, it exists in a superposition of states. It's not in one definite state or another, it's in a combination of many states at once. But when you make a measurement, the superposition collapses and you get a definite result. This is called the measurement problem, and it's one of the deepest puzzles in quantum mechanics. Now, some people have taken this to suggest that consciousness plays a fundamental role in the universe, that observers are necessary to bring reality into being. And if that's true, then the question of how everything came from nothing becomes even more perplexing. Because if observers are necessary for the collapse of the wave function, for the actualization of definite states, then how did the universe exist before there were any observers? Did the universe exist in some kind of quantum superposition until the first conscious being evolved? That seems absurd. But if not, then what caused the wave function to collapse in the early universe? Most physicists don't think consciousness is necessary for wave function collapse. The dominant interpretation, or at least one of the dominant interpretations, is that decoherence, the interaction of quantum systems with their environment, effectively causes collapse without any need for conscious observers. But there are other interpretations, like the many worlds interpretation, which says there is no collapse at all. Every possible outcome of a quantum measurement actually occurs, but in different branches of a splitting universe. When you measure a quantum system, the universe splits into multiple copies, one for each possible outcome. And you, as an observer, go along one particular branch, experiencing one particular outcome, while other versions of you in other branches experience different outcomes. The many worlds interpretation is, well, it's wild. It's saying that every quantum event, every moment where multiple outcomes are possible, the universe splits into multiple copies, and all outcomes are realized in different branches. That means there are an unimaginable number of parallel universes, constantly branching and diverging. And if that's true, then the multiverse isn't just a collection of distant bubble universes created by inflation. It's also a collection of constantly branching quantum universes right here all around us, splitting off at every moment. We can't see these other branches because they're causally disconnected from us. But they're as real as the branch we're in. Now, I'm not saying the many worlds interpretation is correct. It's one interpretation among several, and we don't have a way to empirically distinguish between them. But it's worth considering because it shows just how strange the implications of quantum mechanics can be, and how deeply our question about the origin of everything connects to questions about the nature of reality, the role of observation, the structure of existence itself. And here's where I want to tie things together, because we've journeyed through a lot of ideas, from the Big Bang to inflation, to quantum mechanics, to the multiverse, to the measurement problem, and you might be wondering how it all connects. The connection is this. When we ask how everything came from nothing, we're asking about the fundamental nature of reality. We're asking about the ground floor, the ultimate foundation. And what modern physics tells us is that reality is far stranger, far more subtle, far more surprising than our everyday intuitions suggest. The universe didn't just pop into existence fully formed. It emerged, it evolved, it unfolded according to laws that themselves might be contingent. And the boundary between something and nothing is not as sharp as we think. The quantum vacuum is not empty. Space-time is not a static backdrop. Existence itself is dynamic, fluctuating, creative. And maybe that's the answer, as unsatisfying as it might seem. Maybe the universe came from nothing because nothing, in the absolute sense, is impossible. Maybe the quantum fields the laws of physics, the potential for existence, these are built into the fabric of reality in such a way that they can't not exist. Maybe the question, why is there something rather than nothing, is like asking, why are there true propositions rather than only false ones? Because the existence of truth, the existence of possibility, the existence of being, these might be necessary features of reality, not contingent facts that require explanation. Or maybe not. Maybe the ultimate explanation lies beyond physics, in the realm of metaphysics or theology. Maybe there is a necessary being, a ground of existence, something that exists by its own nature and gives rise to everything else. Maybe the quantum fields emerge from something deeper. Maybe consciousness plays a role we don't yet understand. Maybe there are aspects of reality we haven't even begun to conceptualize. The honest answer is, we don't know. We've made extraordinary progress in understanding the physical universe, its history, its structure, its laws. But the ultimate question of why there's a universe at all, why existence rather than non-existence, that remains open. And, I think that's okay. I think it's even appropriate because we're finite creatures, limited in our perspective, our understanding, our cognitive capacities. We've only been doing science in any systematic way for a few centuries. We've only understood quantum mechanics for about 100 years. We've only known about the Big Bang for about 90 years. We're still at the very beginning of our journey of understanding. And the fact that we've come as far as we have, that we can peer back to the first moments of the universe, that we can describe the behavior of particles and fields at the smallest scales, that we can make sense of the large-scale structure of the cosmos, that's extraordinary. It's a testament to human curiosity, human ingenuity, human rationality. But we shouldn't expect to have all the answers. Not yet, maybe not ever. There might be limits to what we can know, built into the structure of reality itself. The universe might be fundamentally mysterious in ways we can't overcome. And that's not a reason for despair. It's a reason for humility. It's a reason to approach these questions with wonder and awe and respect for their difficulty. So when someone asks you, how did everything come from nothing? You can tell them about the Big Bang, about inflation, about quantum fluctuations, about the cosmic microwave background, about the expansion of the universe. You can tell them about the quantum vacuum and virtual particles and the zero-energy universe. You can tell them about eternal inflation and the multiverse and the anthropic principle. You can tell them about the profound discoveries of modern physics and cosmology, but you should also tell them that the ultimate question, the deepest why, remains unanswered. And maybe that's as it should be. Maybe the universe is supposed to be a mystery, something that invites our exploration, our questioning, our wonder, without ever fully yielding to our understanding. There's something profound about living in a universe we can question, but never fully comprehend. It keeps us humble. It keeps us curious. It reminds us that we're part of something vast and ancient and strange, something that existed long before we did and will continue long after we're gone. And yet we have the privilege, the extraordinary privilege, of being conscious, of being able to ask questions, to seek understanding, to peer into the cosmos and ask where we came from and why we're here. And that's what I find most moving about this whole question of how everything came from nothing. Not just the scientific answer, though that's fascinating and profound, but the fact that we can ask the question at all, that we can wonder, that we can use reason and observation and mathematics to push back the boundaries of ignorance and build a coherent picture of cosmic history, that we're the universe becoming conscious of itself, asking about its own origins. Carl Sagan once said, "We are a way for the cosmos to know itself." And I think that's exactly right. We're not separate from the universe, looking at it from the outside. We're part of it. We're made of atoms forged in the hearts of stars. We're patterns of matter and energy, temporary structures in the flow of cosmic evolution. And yet we can think, we can question, we can understand, at least partially. We can trace our origins back through the history of life, back through the formation of planets and stars and galaxies, back to the Big Bang itself, back to the moment when time began and everything came from something that looks an awful lot like nothing. And in doing that, in asking that question and pursuing that understanding, we're participating in one of the most ancient and noble human endeavors, the quest to understand our place in the cosmos. Every culture, every civilization has had its creation myths, It's stories about how the world began. The ancient Babylonians had their Enuma Elish. The ancient Hebrews had Genesis. The ancient Greeks had their Theogony. These were attempts to answer the same question we're asking: where did everything come from? But what makes the modern scientific answer different is that it's not just a story. It's a model, tested against evidence, refined through observation and experiment, built on mathematics and physics. It's a story that's constantly being revised and improved as we learn more. It's not handed down from authority and accepted on faith. It's discovered through inquiry and validated through testing. And that makes it, in a sense, a collective achievement, a product of countless scientists and thinkers over many generations, all contributing pieces to the puzzle. When I think about the history of cosmology, when I think about people like Hubble and Gamow and Penzias and Wilson and Goethe and Hawking and all the others who've contributed to our understanding of the universe's origin, I'm struck by how much we've accomplished. A century ago, we didn't know there were other galaxies beyond our own. We thought the Milky Way was the entire universe. Now we know there are hundreds of billions of galaxies, each containing hundreds of billions of stars, scattered across a cosmos that's been expanding for nearly 14 billion years. That's a revolution in understanding comparable to the Copernican revolution, to the realization that Earth is not the center of the cosmos. And we're not done. The next century of cosmology will surely bring new surprises, new discoveries, new revolutions in understanding. We'll probe deeper into the nature of dark matter and dark energy, those mysterious components that make up most of the universe but that we barely understand. We'll test theories of quantum gravity and look for signatures of the multiverse. We'll refine our measurements of the cosmic microwave background and search for gravitational waves from the early universe. We'll build more powerful telescopes and more sophisticated detectors and continue to push at the boundaries of what we can observe and understand. And maybe, just maybe, we'll get closer to answering that ultimate question of why there's something rather than nothing. Maybe we'll discover a deeper level of reality, a more fundamental layer beneath the quantum fields and the laws of physics. Maybe we'll find a theory of everything, a single unified framework that explains all the forces and particles and constants of nature. Maybe we'll understand how the laws of physics themselves came into being. Or maybe we'll realize that the question doesn't have an answer, at least not in the sense we expect. Maybe the existence of the universe is a brute fact, something that just is without further explanation. But whatever we discover, whatever we learn, the journey itself is worthwhile. The quest for understanding, the pursuit of knowledge, the attempt to make sense of our existence, these are what make us human. They're what separate us from other animals, what give our lives meaning and purpose. We're not content to just exist. We want to know why we exist, where we came from, what it all means. And even if we never find complete answers, even if some questions remain forever beyond our reach, the asking itself is valuable. Because in asking these questions, in pursuing these mysteries, we're affirming that truth matters, that understanding matters, that reality is worth investigating. We're saying that the universe is not arbitrary or capricious, but orderly and comprehensible, at least to some degree. We're expressing faith, not religious faith necessarily, but epistemological faith, faith that the universe can be understood, that our minds are capable of grasping at least some of its truths, that reason and evidence can guide us toward knowledge. And that faith has been vindicated again and again throughout the history of science. Every time we've asked a question about nature and pursued it rigorously, we've found answers. They're not always the answers we expected. They're often stranger, more subtle, more surprising than we anticipated, but they're answers nonetheless. The universe yields its secrets slowly, reluctantly, but it does yield them to persistent inquiry. So how did everything come from nothing? The scientific answer, incomplete and provisional as it is, goes something like this. Approximately 13.8 billion years ago, the universe began in an extremely hot, dense state. We call this the Big Bang, though it wasn't an explosion in space, but the beginning of space itself. In the first fraction of a second, the universe underwent a period of rapid inflation, expanding exponentially due to the energy of a scalar field. As it expanded, this field decayed, releasing its energy as matter and radiation, reheating the universe. As the universe continued to expand and cool, particles combined to form atoms. Atoms gravitationally collapsed to form stars. Stars grouped into galaxies. Planets formed around stars. and on at least one planet, life emerged and evolved and became conscious. And the initial state from which all this emerged, that incredibly hot, dense, highly ordered state at the beginning, it may have arisen from a quantum fluctuation in a pre-existing quantum field. The quantum vacuum, despite its name, is not truly empty. It's a seething foam of virtual particles and fluctuating fields. And under the right conditions, a fluctuation in this vacuum can nucleate a bubble of space-time that expands and becomes a universe. This doesn't violate conservation of energy because the total energy of the universe, including the negative gravitational potential energy, may be zero. The universe could be, in effect, the ultimate free lunch. But this explanation assumes the existence of quantum fields, the laws of quantum mechanics, the potential for space-time to exist. Where did those come from? That's where our current understanding reaches its limit. We don't know. We have speculations, mathematical models, philosophical arguments, but no definitive answer. The ultimate ground of existence, the reason why there's a how at all, remains a mystery. And maybe it always will, or maybe future generations will crack this puzzle too. Will push understanding to an even deeper level. We can't know. What we can do is continue the quest, continue asking questions, continue pushing at the boundaries of knowledge, because that's what we are, that's what we do. We're the universe's way of understanding itself. And in that understanding, however incomplete, however provisional, however fragile, we find meaning, purpose, wonder. The universe came from nothing, or from something very much like nothing, something that we can barely conceptualize, something that challenges all our intuitions about how reality works. And that's the story of existence, as best as science can tell it, a story of quantum fields and fluctuating vacuums, of inflation and expansion, of cooling and structure formation, of stars and planets and life and consciousness, a story that begins in mystery and leads through a long chain of physical processes to us, here, now, asking where we came from. And in the end, perhaps the most important thing is not the answer, but the question, not the destination, but the journey, not the final truth, but the pursuit of truth. Because we're finite beings in an infinite cosmos, and we'll never have all the answers. But we can keep asking, keep wondering, keep seeking. And in that seeking, in that endless pursuit of understanding, we transcend our limitations. We become more than just collections of atoms obeying physical laws. We become questioners, thinkers, understanders. We become human. So the next time you look up at the night sky, at the stars scattered across the darkness, remember that you're looking at the aftermath of creation, at light that's traveled across billions of light years to reach your eyes. Remember that every atom in your body was forged in the heart of a dying star, that you're literally made of stardust. Remember that the universe began as something smaller than an atom and expanded to become this vast cosmos. Remember that everything you see, everything you are, came from nothing or something like nothing in a process that we're only just beginning to understand. And let that fill you with wonder. Let it humble you and inspire you and motivate you to keep questioning, keep learning, keep pushing at the boundaries of understanding. Because that's the greatest gift the universe has given us. Not just existence, but the capacity to wonder about existence, to ask why we're here and where we came from and what it all means. And in asking those questions, in pursuing those answers, we participate in the universe's ongoing project of self-understanding. We become, for a brief moment in cosmic time, the way the universe thinks about itself. And that's something. That's really something. Out of nothing or something like nothing came everything. And part of that everything is us. Conscious, questioning, wondering, beings who can look back at the origin of existence and ask how it all began. And even if we never fully answer that question, even if the ultimate mystery remains, we're privileged to be here, to participate in this grand cosmic story, to be alive and aware in this strange and beautiful universe that somehow came from nothing at all.